All right, let's dive right in. I want to talk about strain wave gear reduction and cross roller bearing technology and the synergy between these two technologies. The benefits of strain wave gear units integrated with cross roller bearing support. Here we have an image showing the three components that make up a strain wave gear train. And this is what I would refer to as a component set. Component set comprised of three elements, one being the circular spline on the far left, the flex spline in the middle, and the wave generator on the right. Strain wave gears are basically zero backlash, high precision gear reduction mechanisms, and they consist of these three elements. The wave generator is basically an elliptical plug with a thin-raced ball bearing pressed around it. And when the wave generator is inserted into the flex spline, which is a steel cup with very thin walls and an external gear, the flex spline takes the shape of the elliptical bearing. And when the flex spline is then inserted into the circular spline, we have the complete gear set. So the principle of operation, basically it involves a traveling deflection wave. The circular spline, which is the internal gear, they've got internal gear teeth. Go back to where I was there. And the circular spline has two more teeth than the flex spline. So for every rotation of the wave generator, it causes the flex spline to advance two gear teeth. Okay? So basically, the mechanism is an ellipse running inside of a circle. And the elliptical shape of the wave generator causes the flex spline to engage with the circular spline at two opposite regions across the major axis of the ellipse. Key attributes of strain wave gearing, number one is zero backlash, no play in the gear train at all. Provides very high accuracy. Positional accuracies are on the order of sub 1 arc minute. Repeatability is in the range of plus or minus 5 arc seconds, so it's a very repeatable gear train. And a single gear pass can span ratios from 30 to 1 on the low end up to 160 to 1 on the high end. That's for industry standard ratios, but for custom engineered solutions, you can get ratios as high as 320, 400 to 1. The lightweight, whoops, I did again. The lightweight is a very valuable parameter, especially if you're on end-of-arm tooling and you might be looking at a 7-axis robot and the last 4 axes are out at the end of arm. You want it to be as light as possible. Additional attributes, it's a very power-dense technology, a lot of torque per envelope. It's torsionally stiff, and that's a result of large tooth contact ratio. About a third of the teeth are engaged at all times, and it's got a relatively large pitch circle diameter, so that gives you good stiffness, good power density. You can get high reduction ratios. As I said, 160 to 1 is industry standard. But you can get as high as 400 to 1 in a single pass. The device is back drivable. The back drivability characteristics generally are published, so you know what the breakaway torque is going to be needed to get the device in motion. And when using component sets, it's highly customizable. If you're looking to really tightly integrate the component sets into a robot arm, you can machine all sorts of different features into the strain wave components to make it more compatible with the design. Whoops. Excuse me. Okay. See if we can get my cards in order here. Okay, strain wave component sets. Here's several different images of what component sets and higher level gear units would look like. Over here we've got the component sets as individual components. Here it's assembled. And then these images here are higher level assemblies where we integrate cross roller bearings. As far as component set alignment, if you're integrating component sets into higher level systems, it's very demanding in terms of assembly tolerances. There's a lot of concentricity and parallelism requirements that you really need to hold tolerances on the order of microns in order to get the device to function optimally. So if you're really looking to maximize accuracy, repeatability, obtain the stiffness levels that you're expecting, it really requires that all the mating parts have very good parallelism, perpendicularities, concentricities, so you can ensure that the components are aligned. So in order to solve that challenge, we have gear units with integrated cross roller bearing. And basically what the cross roller bearing does is allows you to align the circular spline and the flex spline and keep everything perpendicular and concentric, and takes the challenge of meshing those parts away from the designers. You just basically bring in a device that's already aligned, already assembled, and you're ready to go. So with gear units with integrated cross roller bearing, you're basically looking at a partially assembled joint. The design and mating parts fabrication is simplified, and you've got really good, accurate, and rigid alignment of the flex spline and the circular spline. So if you procure a gear set with a CRB, it takes away a lot of that difficulty. There's still some tight tolerances you need to hold on mating parts as you're bolting the load to the output face of the device, or as you're mounting a motor to the input side. But it's a lot less stringent requirements than if you're working with component sets. Just want to talk a little bit about the service life of strain wave gearing. It's mainly driven by the wave generator bearing. The wave generator bearing is basically a ball bearing, so the service life of the strain wave gear follows a cubed root equation where you've got the rated torque over the average application torque cubed times the rated speed over the average speed. So it basically follows this curve here. And if you're looking at the flex spline fatigue strength, that follows this curve here. And as long as you stay below the momentary peak torque rating, the fatigue strength of the flex spline is infinite. Just a little more about service life calcs. To calculate the average load torques, you're basically looking at a cubed root equation. And for the average speed, basically speed times time over the total time. So you're basically plotting a torque profile over time and also a speed profile over time, and crunching the numbers to determine what your average load torque and your average speed are. Moving on to the cross roller bearings. The service life of a cross roller bearing is something that has to be calculated independently. There are three primary characteristics that you're considering when you're looking at cross roller bearing service life. Number one is the maximum moment load on the bearing. The other is the service life calculation. And then third would be something called the static safety coefficient. So just looking at those individually, maximum moment load, that's a calculation based on the maximum radial force plus some distance, which is basically the distance from the center of the CRB raceway to the mounting face, and then from the mounting face to the location of the load. And then the axial component of force, that would be this guy over here, and its respective distance from the center of rotation. So just looking at what a moment load is, basically this is the cross roller bearing output of a strain wave gear train, and when you apply a what's called a tilting moment to the rotating output flange, you get this moment load. And the image here on the left is basically the cross roller bearing with their reaction forces being drawn in. So you can see what kind of loads and where they are in terms of the maximum stress on the rollers. As far as the service life calculation of a cross roller bearing, it's basically calculating the radial load and the average axial load. And there's a coefficient X and Y, which basically talks about the orientation of the loads relative to the bearing. But basically, L10 life calculation is a 10/3 root of the basic load rating divided by the application load. And then the CRB static safety coefficient. Basically, this is a ratio of the basic load rating over the application load, where this is the amount of force put on the bearing to just before it starts deforming permanently. So what you want to do is take a look at this ratio, and under normal operating conditions, you want it to be about 1.5. When there's a lot of shock and vibration, you want it to be a little bit bigger than 2. And when the highest rotational position is required, you want that ratio to be above 3. Fortunately, all of those equations that we just went over, you don't need to remember any of them. There are a lot of sizing software products that are available on the market. I particularly like this one. It's called ServoSoft. It allows you to build inertias, define motion profiles, choose products, including drives and motors and gearboxes, ball screws, lead screws, roller screws, rack and pinions, all different types of mechanical solutions you can choose from databases and drop them into the software and see how things play out in terms of ratio selection, pitch diameters, all different types of parameters that you can play around with to optimize the system. In this particular case, I just built an inertia. I chose a mechanical system, which is a rotary turntable in a vertical axis, and I built an inertia on the output, which consisted of several different shapes, some cones, some blocks, some cylinders, and I used all different densities, so I would create a very unbalanced load to see how the cross roller bearing can support that. So I also built a trapezoidal profile, and you can see in the plot here, the blue is the velocity. This would be the output velocity of that turntable, and then the red plot here would be the position of the turntable. So with that said, I also selected a 2-inch pitch diameter strain wave gear with 160-to-1 reduction ratio and a cross roller bearing on the output face. And the results, as you can see from the chart here, all of the gearing loads are within the continuous duty portion of the curve, which makes it very well sized. So this is looking at the gearing ratings and the utilization of the gearing. And as you can see, we're using 17% of the maximum output torque, 37% of the maximum speed, 31% of the root mean cubed torque, and 46% of the mean input speed. So all of our parameters are in the green, and we're feeling pretty good about this selection. But in addition to looking at the gearing capacity, we also need to take a look at the cross roller bearing ratings and their utilization. In this particular case, as you can see here, these are the application loads, well within the specified range of the cross roller bearing on this assembly. And as you can see, we're using about 46% of the axial load capacity, about 36% of the radial, and about 33% of the maximum tilting moment. So very well sized solution here, and I would fully expect that a product that shows these types of utilization would have service life in the 100,000 hour area. Actually, in this case, 75,000 hours. The other big advantage with cross roller bearing integrated strain wave gears is sealing. Strain wave gear units with integrated cross roller bearings generally will have at least one output seal on the output face of the device, although this particular one is completely sealed. This one as well. This one here is sealed on the output side, but you need to seal it on this side as well. And on this guy here, the sealing needs to be done on this side where you'd generally be mounting a motor. Lubrication of strain wave gears is absolutely mandatory if you're going to achieve maximum performance and to meet your expected service life goals. Sealing does a couple of things. Number one, it prevents grease leakage, so it ensures that you've got lubricity where you need it. But it also keeps the environment from getting debris into the gear train or into the cross roller bearing, which is also detrimental. So if you were working with component sets, you would need to build all of this into the product. But if you were to source a strain wave gear with an integrated cross roller bearing, you're halfway there to building your actuator already. The integrated cross roller bearing gear unit sealing, there are a few different areas that are critical to make sure surfaces are lubricated. First up would be the toothing, which basically would be the gear mesh between the flex spline and the circular spline. Also important is to lubricate the interface between the flex spline and the wave generator. Very important that those surfaces are lubricated and remain lubricated during operation. And then thirdly, the wave generator bearing, basically the balls, the raceways need to maintain lube. If any of these areas are starved of lubricant, it's going to significantly reduce the service life of the product. Gear units with integral CRB has a level of sealing already built into the design. So here you can see on the left side of this cross section, the cross roller bearing is here and here, and right next to it is the output seals. Okay, so this whole side of the device is already sealed up, ready to go. Over here on the right side, this is where you'd be mounting your motor, and the recommendation would be that you have O-rings or some kind of sealant on the flanges to make sure that you're keeping debris out, keeping lubrication in. Here's another example. This is another integrated cross-roller bearing gear unit. This is a thin profile, what we'd call a dish strain wave gear set. Over here you can see cross-roller bearing, and over here is where you've got your seal. So again, keeping lube in, keeping debris out, and just really simplifying the overall assembly, and pre-aligning flex spline to circular spline. Cross roller bearing attributes. First one up, I'd say, is going to be high rotational accuracy. If you're looking to build a high precision turntable, for instance, a cross roller bearing is a great bearing system to accomplish that. As you can see here, the bearing elements are crisscross arranged, and they provide good moment loading, good tilting moment capacity, and able to react to loads in all directions. Cross roller bearing offers a very compact design. You've got the crisscross rollers sharing a raceway, and you don't have spacing between the bearings, so it keeps it nice and thin, but also nice and stiff, and very good, smooth, low friction motion. High rigidity, that's obviously another advantage. You don't want too much deflection as the output flange is supporting the load, and cross-roller bearing accomplishes that. Multi-directional load support, so you basically can have axial loads, radial loads. They can be offset and changing over time. Maybe the introduction of tool pressure, things like this come into play, and the cross-roller bearing reacts very well to that. And lastly, smooth motion. CRBs running in ground raceways run very smoothly and don't deflect very much under heavy loads, so they just give good smooth motion. Other advantages, attributes of CRBs, reduced assembly time. Like I said, if you're trying to integrate a flex spline and circular spline and wave generator, it's nice to have that already pre-aligned with a cross-roller bearing. Long service life. Again, if the product is sized properly and the application loads are below the rated loading of the product, and if you're able to maintain good lubricity, you're going to get good long service life. Improved responsiveness, that has to do with stiffness, low maintenance. These bearings are lubricated for life, and they're just ideal for building compact actuators and rotary tables. CRB design and construction, basically you're looking at orthogonal roller arrangement. The raceways are hardened in precision ground, generally induction hardened, zone hardened, if you will, so kind of leaves the rest of the CRB a little softer, which allows you to machine it and do some special things with it. The rollers have retainers that keep the rollers from bouncing into one another, makes it nice, smooth, frictionless motion. They've got a very high roller length to diameter ratio, and they're preloaded. So, if you get a slight preload, 1%, 3%, you've minimized deflection when you start loading it up. And here I'm just going to take a quick look at a couple of different robot joints. First one up is a rotary joint using a gear unit with an integral CRB. In this image here, you can see the CRB is on the bottom here, facing down. The output seal is here, containing lubricant, and the input face up here is where you've got a motor mounted. I'm sure over in these areas here there is sealant being used to make sure that lubrication remains inside the device. And this robot joint is a wrist joint with two axes. The primary axis up front. Here again, cross-roller bearing on the output facing down, and right next to it is its seal. And again, containing lubricant. Up top, there's also some sealing done as well to make sure that the lubrication stays inside the wave generator bearing, between the wave generator bearing surface and the flex spline surface, and also in the gear teeth. The second axis is driven through a spiral bevel gear pass. That input shaft comes right through the hollow bore of the first unit and comes through a one-to-one pass into the strain wave gear set coming out of the device. And in this case, again, cross roller bearing driven or supported, output seals right next to it. And so basically you've got one axis rotating in this orientation and then this axis rotating in this orientation. So again, another example of how a cross roller bearing supported strain wave gear set provides a nice compact solution and makes assembly much easier with the pre-aligned component sets. And with that, I'm going to open up the floor to any questions anybody might have.